Hello and welcome to week 14. My name is Mildred. This week we are going to look at the maximum flow problem. Now, the maximum flow problem is a fundamental problem in the graph theory in which we try to find the maximum flow through a directed graph. And now, for this to make sense, we have to understand where this is needed or in what scenario we need this maximum flow problem. When we do supply chain, when we want to have like the maximum goods delivered or a network bandwidth, we want to get the maximum data flow through a network, or water pipelines, we want to see the maximum water delivered to a city, so things like that. So whenever we have a directed graph, we want to say each edge has a capacity, and that capacity is the maximum amount of flow that it can carry. Now there is a source node, we'll call this source node S, and that is where the flow originates, and then there is a sink node called this T, where the flow terminates. Now the objective is for us to determine the maximum flow from S to T that satisfies the constraint, which is the capacity constraint that we have, right? So every time we have a flow network, it is directed, each edge has the capacity constraint, and the current flow will initially be set to 0. Then we always want to get the residual capacity, which will be like the remaining capacity, and it's going to be the capacity minus the flow. We want to have the graph showing possible additional flows and also augmenting paths from S to T with available capacity. Now, the core rules that we want to make sure we follow is that the flow on an edge is less than or equal to its capacity. For every node we have, apart from the source node and the sink node, which is S and T, the incoming flow must be equal to the outgoing flow, and then the maximum total flow from S to T is what we want to get. Okay, so the fundamental idea behind the max flow algorithms is to start with 0 flow, then find an augmenting path from S to T, then push as much flow as possible through that path, and then update the residual path and repeat until no augmenting path exists. We have 2 algorithms that we will consider. There are more algorithms, or there is a more advanced algorithm that we are not going to look at here. We have the forward focusing algorithm, which can be slow or infinite with irrational capacity. So we're not going to illustrate that. We're going to look at the Edmonds cap algorithm, which is more improved than the forward focusing algorithm. And we are going to use the adjacency matrix or adjacency list. We're going to use Q for the breadth first search, and then we'll reconstruct the paths using the parent array. So the first thing we want to do is we have a graph like this. We want to have a matrix where when we have the graph of U, P will be equal to the capacity. That is what we want to represent. So let's say we are going to use this graph, this matrix. We want to first of all find an augmenting path, and for us to find this using the Edmonds caps algorithm, we use breadth first search. So let's import from collections, import TQ. Now we want to, let's say the BFS, we want to find augmenting, and when we are traversing, we want to get a residual. We want to also have the source. We want to have a sink where it terminates, and then the parent. Then let us set visited to be equal to the length of the residual, and we'll set everything to false. So let's say visited is equal to, we want to have a list that is filled with false, and we want all the items to be the length of the residual like this. Now let's create the Q is equal to the Q, and we say that we are going to get the source first. So with the Q source, which is the start, once we are starting from the source, visited source, let's set it to true. So let's say visited source will now be equal to true. Okay? Now let's loop through this Q, and we want to traverse through all of the nodes. So let's say while Q, and we'll set U, let's set the vertex U is equal to Q dot pop left, and then we'll say for V in range length residual, if not visited E and residual U V is greater than 0, Q dot append V visited V equal to true, and then parent V is equal to U. And now we're going to say if V is equal to sink, if it's like the way it terminates, we'll return true. So we'll say if V equal to sink, return true, and if not, we just return false like this. Now we want to now get the maximum flow using the Edmonds caps algorithm. Now we'll say that we can do this with classes, but I'm just trying to make this like functional programming. So we'll say Edmonds cap, and I will pass in the graph, I will pass in the source and the sink. So the argument we'll pass in is graph, source, sink. Now we want to get the length of the graph. Let's store it in N as N graph, and we want to say let's select all the elements of a list so that we're creating a shallow copy. So we'll do residual is equal to S row, and here I'll just use a colon to denote I'm from taking everything from start to end from for row in graph. Now let's get the parent, and we'll say the parent is -1. So we're filling the list with -1 times the length of the graph, right? And then the max flow, we always start with 0 is equal to 0. Now we want to get an augmented path. We'll use the breadth first search here. So we'll say while, so let's say PFS, and we'll put in the residual, the source, the sink, and the parent. Say path flow will now be equal to, let's use positive infinity like this, and V is equal to sink. So let's find the bottleneck. Let's say while V is not equal to the source, then we'll say U will be equal to parent V. Now we'll say the path flow will now be equal to the minimum path flow residual UV. Now let's say V is equal to U, and we want to now update the residual capacities. So say V is equal to sink, and we'll say while V is not equal to the source, U will be equal to parent V, residual UV minus equal path flow, and residual VU plus equal path flow. And now we'll say U is equal to V, and max flow will now be plus equal path. Then we'll return max. Okay, so what we have done here is we are trying to use the Edmond-Capps algorithm, and what we intend to do is to find the path using breadth first search here. We'll get the bottleneck capacity, which will be equal to the minimum, all right, the minimum of path flow and the residual. Then we push the unit of flow and we'll update the residual graph. So let's test this to see if this is correct, and then in the live web conference we're going to use a real world scenario to make this make more sense. So let's say the source is equal to 0, and let's say the sink is equal to 3, right? So we'll use this graph. Let's say source 0, sink 3. We're going to use this graph, and we're going to say let's print maximum flow, and we're using the Edmond-Capps algorithm. So we'll say Edmond-Capps, we want to supply the graph, then we have the source, and then we have the sink. So if all is well, we're expecting that we get the value. So when I run this, so let's look at how we get this one. Residual, this is not covered properly, so I save this, I run again, and I have to delete all of this here to make this work properly, and I will clear this, and then I will run. We have this running endlessly. Maybe we have an endless loop. Let me see what the problem might be. So here I'll do, there is V equal to U. This is where the problem was. And so when I run this again, we have the maximum flow is 15. All right, so the max flow is 15. We are going to look at step by step a visual explanation of each of these steps that we have performed for better understanding in our live web conference. We can try to design an emergency medical supply distribution system where we have a roads that have limited capacity or number of trucks that can flow through that road in a day, and we want to build something where we can use this Edmond-Capps algorithm to guarantee optimal flow, and we have a predictable runtime, and we want to use that for logistics planning. So it's basically what we just already did here, but in our live web conference, we'll give a better explanation to all of what we have done here. So if I say, for instance, let me change this. I have this as the graph. So let me remove this. I will delete all of this. Let's say I have this as the graph, and I say, sorry, here is V is equal to U, and then I clear, and I want to use this graph. So let's say here is S, this is A, B, C, D, and this is the terminal T here. And I have that as a graph, and I want to, so I have 0, 1, 2, 3, 4, 5. So we go from 0 to 5. Let's say, so I'll say we have sink is equal to 5 here. So 0, 5. So I'll use this, and when I run this, we should get about 20 to 25 thereabout, and we have 20. The maximum flow is 20. And what this will mean, if like we're trying to do how many truckload per day or the road expansion for new routes, we know that it's 20 that we can use. So the bottleneck detection that we'll have here is we want to go from depot, let's say A to C. It is going to be saturated, and so we're going to look at a detailed explanation of all of this in our live web conference. Thank you, and see you next week.